All this stuff should be familiar. Nothing's changed here except office hours. And that's also on that first handout with all the pretty colors on it. My Zoom only day is going to be on Wednesday morning. Rest of the time, office and Zoom. But if this is your only class, well, let me back up. If you're on campus, check, see if I'm in my office. If you're gonna make a special trip, as usual, give me a text or something, so be sure I'm here. I never know. Okay. Let's see. Everybody's got Cengage from last semester? Good. That's the cheaper way to go. Okay. There's no final exam. Did we have a final exam last year? Yeah. There's not enough time for a final this time. So we'll, your exams are just chapter exams. That's 70% of your grade. Homework is still 20%. You get credit for attending. Crosswords are the same as before. Why did I put 10%? Usually I make crosswords one exam grade. That probably is one exam. How many exams do we have? Let's see. Going. Here we go. 1, 2, 3, 4, 5, 6. Yeah, okay. That makes sense. Crosswords are worth an exam. Let's see. You probably got everything else you need: calculator, lab coat, safety glasses if you want them. And we'll go over that lab in a minute. Let's see. So probably want to focus on the schedule so you keep up with everything. I put chapters 10 and 11 lectures in next week, but I think we're going to have time to get chapter 10 today. And then that'll loosen up next Monday. We're not going to have a lab until the 10th of February. So I think next week I'll take that lab and we'll go through it as a introduction, pre-lab introduction. So our first exam is on the 17th of February. That means we're going to have a review on the 10th, same day we have the lab, and that's the pattern. It should be the pattern. Review days will be lab days. I'm just checking to be sure if I'm correct. Yeah. The only problem is we're going to run out of time at the end of the semester. So the chapter 18 is getting squeezed. So we're going to have May 5th, we're going to have an exam, and then I'm going to give you material on chapter 18, electrochemistry. And I'm not sure if this lab, this electrochemistry lab, is going to be viable or not, because you get the lecture after you have the lab. But the lab is informal. So that's, in fact, that's the only informal lab, is the electrochemistry lab. The rest are formal reports. Let's see what happens through the semester. So that means that electrochemistry review is going to be in Brightspace. So after you get the lecture, do the homework, do the review in Brightspace, then be ready for exam during final exam week. Okay, any new stuff here? I don't see new. That's all typical stuff. Office hours, homework. If you get into Brightspace and you click on go into, say, like module 3, for instance, and you click on the homework for module 3 and it doesn't connect you, let me know. Because that's one thing that sometimes doesn't carry over from one from the last semester that we did this copied into this semester. Those links may be broken. So I might have to fix them. I'm pretty sure the first and second modules are working. Okay. I still have option for taking exams in Brightspace if you can't make the class that day. Okay, any questions? That was pretty easy. Get this up out of the way. All right. Let's see. You'll notice that in the handouts, chapter 10 and the review that goes with it are separate from chapter 11. And you noted rightly that later on we have another 2 chapters. These 2 chapters, 10, 11 are exam 1, 14, 15 are in that one exam because they're both on pH, acid equilibrium. So they'll probably be separate reviews also. But when we do the review in class, I will have combined them into a single document so that I won't have to reload and share. Okay. So let's look at the lab. Call it that one. We'll talk about the lab a little bit. We'll just get that done. Did you pick up lab documents? I don't think you did. You didn't get lab documents. The only reason there are only 3 in this set because you guys have been here before. And you probably got all that other crap that I normally give you. And if you've lost it somewhere, then copies are in Brightspace, such as sample lab notebook, sample reports, stuff like that. Okay, let me go down to, yep. You know what? It might be better. Has everybody been into the Brightspace and looked at both 102 and 104 in Brightspace? Just to see if anything is out of place. Okay. It might be better just to go in rather than share this, is to share a browser and look at, where is my browser? Here it is. We'll just go into Brightspace here. Find it. There it is. Okay, anytime now. You'll notice Brightspace has been slow. Yeah, just within right about the beginning of the semester, it just got sluggish. I'm gonna blame it on WVNet. Yeah, I'll go for that. Okay, let's see. 22H, no, that's physical science. Here we go. That's 102. 104. Here we go. 22572. That's it. All right. I didn't mention earlier. I didn't put it here. In 102, I've got contact information for Barry Pine, our physical science tutor. If you need any help, if you need somebody else to explain it rather than me, sometimes you hear it from some different angle. It makes more sense. So let's go to content. Here we go. All right, and it's as usual. Start here. There's a syllabus and lab schedule. That's nothing new. Shrink that down. There's a safety contract. You can turn that in next week if you want. It's as usual. There are 2 copies. Fill out both of them and hand me one of them. Notebooks, reports, instructions. There's everything you need to know. I don't think that's going to be a problem for this class. Everybody sort of got the hang of it toward the end. Okay. What else do I want to get into? Here we go. Exercises. All right, so our first exercise is going to be, well, the first lab notebook check. Does anybody need a lab notebook? No? Good? Okay. Because I still have a stash. Set up your lab notebook according to this plan. And the first lab notebook check will be the usual. Just set it up and number every page. Okay. Then for each lab, I'll follow the same pattern and check your lab notebook before you do the lab. And if I can't give you an 80% on that preparation, then you can't do the lab. Okay. I was a little too lenient last semester. I think I need to be, for safety's sake, you need to know what you're going to do. Let's see. Oh, wait a minute. Le Chatelier's principle, that's also an informal lab. Okay. And the last one, electrochemistry, is informal. So we have 1, 2, 3, 4 formal reports. It's not too bad. First one's going to be molecular weight by freezing point depression. Everybody knows freezing point depression if you've ever made ice cream. Right? Ice cream won't freeze unless you get it really cold. Well, you got to get it colder than water, ice. So what do? You add salt. And that decreases the freezing point of water by dissolving a solute in it. I'll talk about that in more detail later. Oops. Is that a video demonstrations? Do I want you to see that? No, maybe I better not. Because we're looking at it from the instructor's viewpoint now. So you'll see some stuff that you probably shouldn't see. Okay. Well, I don't have anything else to say about that. The rest of it is dictated by the school that I put in there. Academic calendar. I wouldn't trust that academic calendar link because they changed it. The one that's connected through our website actually puts the spring semester starting before Martin Luther King. And they sent out another one, but didn't correct it in the website. So if you need to answer any questions on spring calendar, just go to the syllabus. All right. Let's see. I don't think we'll have any trouble with administrative withdrawal. I have notebooks. Okay. Any questions? Maybe Madison really is sick. She's not on yet. All right. So let's get into chapter 10. Get it over with. All right, let's stop this share. And let me share the PowerPoints. We can take a leisurely stroll through liquids and solids. Let's see. Make a slideshow. There you go. In the first semester, we did talk about liquids and solids some. But we didn't go into the kind of detail we're going to go into today. All right. What we're interested in, as far as how liquids and solids get to that phase they're in, we're talking about types of bonding. You can split bonding into two types: the intramolecular and the intermolecular. The intramolecular is within the molecule. So we're talking about largely covalent compounds. In other words, the bonds that hold them together as discrete molecules. The intermolecular bonds, on the other hand, are those molecules that occur between molecules. And we're going to discuss the different types of bonds that can occur, but we're largely interested in the difference between intermolecular and intramolecular has to do with bond strength. The covalent bonds are extremely strong by comparison. The intramolecular bonds, very strong as compared to the intermolecular. And that only makes sense, because what would happen if the bonds between molecules were stronger than the bonds within the molecule? Molecules just get ripped apart, right? If your neighbors are pulling on your atoms stronger than you can hold the house together, your house collapses. It just falls apart. So that's the first overriding principle, is the strength of the bonds. Now, when we get to the point, once we look at attractions between molecules, we're looking at electrostatics primarily. And we divide those into two types: the dipole types, actually three types: the ion type bonds, which are actually not covalent, but they do have a bearing on the intermolecular forces. The dipole forces, let me see, this is going to get convoluted if I don't move on and then come back to this topic. That's what you want to remember. Intramolecular forces holding the molecules together are much stronger than intermolecular forces. Okay. Hold on a second. Okay, I'm going to have to, I don't have a slide on that. All right. So these are covalent bonds, covalent, holding the molecules together. And these are electrostatic. Now, the electrostatic bonds can be, they're based upon the polarity of the bonds. We did cover that last semester, didn't we? Bond polarity. Okay, good. I'll have to go over that again. So if you have a bond that's polar, like for water, for instance, like we know that the dipole moment is going to be toward the oxygen, right? Right? That means an overall dipole is going to be that direction. So this end of the molecule is going to be slightly negative. This end is going to be slightly positive. Okay. And those are not complete electron transfers. These are just redistribution of electron density so that you get a slight negative or a slight positive. Let me use that. When that happens, then if this is a pure substance like pure water, then the molecules are going to align themselves so that the negatives attract the positives. And that's your intermolecular force. So if we have another oxygen over here, like this, like that, then this is going to be slightly negative, that's going to be slightly positive. And you get a dipole-dipole. A dipole from one molecule, the dipole of the other. Now, I kept it simple. This is a pure substance, but this can happen in mixtures also. For instance, if we wanted to make booze, we put ethanol in there. Well, the ethanol molecule has a methyl group, and it has, let's see, 2 hydrogens there, and it has an oxygen here, like that. So there's your dipole for ethanol. And if you put it in aqueous solution, then the same thing, this negative and that positive are going to interact with water in a dipole-dipole interaction. Okay. All right. Within the dipole-dipole is a special class of bonds called hydrogen bonding. And in order to have hydrogen bonding, you need a hydrogen attached to one of the more electronegative atoms. And that includes nitrogen, oxygen, and fluorine. And you'll get the potential for nitrogen, oxygen, fluorine. You'll get the potential for hydrogen bonding. 2 reasons that the dipole is strong is the separation of charges is wider than it is for other types of dipoles. The reason number 1 is the electronegativity of these atoms. Nitrogen, oxygen, fluorine are highly electronegative. Remember, they're in the upper right-hand corner of the periodic table. The other is that hydrogen is very, very small. So that means you can get really close. And remember, the attractive forces are stronger the closer you get. Okay, so those 2 factors contribute to hydrogen bonding. It's still a dipole-dipole interaction. It's just the stronger member of the family. And that's why water boils at 100 degrees Celsius, is that strong hydrogen bonding. If that were not the case, then water should, by the trends of all the dihydrides of its neighbors, it should boil at less than 0. Okay. All right. So the other possibility for the intermolecular forces, if you don't have a significant separation of charge in the bond and in the molecule as a whole, you still have attractive forces, and we know that because of things like nitrogen gas. Right? If you get it cold enough and put it under pressure, it will turn into a liquid. Remember it, and you can only get a liquid when you've got strong enough forces to hold those molecules in closer proximity than they would be in a gas. So we know there are forces involved here, and we've drawn nitrogen before, right? I think. Right, there's nitrogen. There's no possibility of dipole there because these are exactly the same electronegativity. So what is it that's holding them together? Well, that was proposed by a scientist, like his name was London, so he gets the credit. London dispersion force. He calls it dispersion because it's temporary. There's a dispersion of electric charge for a split second, microsecond. So the electron cloud is always in flux, which means that at some point you could get a slight negative on this end and a slight positive on that end. If that happens, then any of its neighbors are going to feel that effect. This negative is going to push electrons away from there, and that positive will pull them over here. So that will give you a slight negative and a slight positive temporarily. And when that happens, you have a temporary electrostatic interaction. And it's not permanent. The dipole-dipole interactions are permanent. But the London dispersion forces are temporary. So that's why they're very, very weak. But they are there. And in fact, London dispersion forces are always there. No matter what the interaction, London dispersion, always there. It's just that if you have dipoles or hydrogen bonding, then they don't matter. They're so weak that you can just ignore them. Okay. You can get the same type of interaction with the noble gases. As you get larger and larger and larger, the noble gases, you get more volume over which you can redistribute the electron density. So the larger ones have stronger London dispersion forces. And you can see that trend. In fact, I may have a table in here. You can see that trend in their boiling points. Boiling points increase in temperature as you go down. In fact, the coldest liquid, the coldest substance that we can make in bulk is liquid helium. It's like 4K is its boiling point. All right. So there's an example of hydrogen bonding for water. We don't have to dwell on that now. All right, the stronger forces, the stronger bonds are intramolecular, that is internal to the molecule. All right, and it's simple logic. If it were the other way around, the molecules would just get ripped apart. Okay, so what do we expect in phase changes? We talk about phases. We've got molecules that are experiencing attractions among the molecules of a pure substance, for instance. That's where we're going to start anyway. So in order to get a phase change, if you go from gas to liquid to solid, the forces that are holding the molecules together have to get stronger, or the energy that's disrupting those potential bonds has to weaken. In other words, get them colder, reduce their kinetic energy, so that the forces that are available to hold them together now can take over. All right, to do a phase change. If you break bonds in a molecule, what are we talking about? We're talking about a chemical reaction, right? And here we're talking about physical behavior, physical change. That's a phase change. So this is the author's idea of representing the difference between gas, liquid, solid. Gases are very far apart. They're moving really fast. You can see their streaks. They're trying to show you they're moving fast. That means they have a lot of energy. And that excess energy is enough to overcome any intermolecular attractions. Well, most of them. If we reduce their kinetic energy, then those forces can take over to make a liquid and hold the molecules close together, but not in a regular structure. Right? They're still not strong enough. But if we cool them down even further, we can reach a regular arrangement of molecules in a solid form. Okay, if we go the other direction, then you add energy and the motion of the molecules increases. They just vibrate if they're a solid, but they vibrate until they can break those intermolecular forces that are holding them together. Then they become liquid. If we go liquid to gas, it takes a whole lot more energy to go from a liquid to a gas than it does from a solid to a liquid. Much, much more. You break any bonds that are holding the liquid together. We also notice change in density also. Now, water is different. Water has a maximum density at 4 degrees Celsius. It would be maximum density for water is 4 degrees Celsius. As we heat it up, its density decreases toward the liquid. And even further toward the gas, density decreases. Density decrease. This direction. And that's typical for solid liquid to gas transitions. But at 4 degrees Celsius, water is not a solid. Right? We got to go down to 0 degrees to get a solid for water. But when that happens, density increases. Oh, excuse me. Decrease this way. It also decreases this way, excuse me. Okay, decreases this way, decreases that way. This is maximum density for water at 4 degrees. Now, the reason its density decreases when it becomes a solid as compared to a liquid goes back to the definition of density, mass per unit volume. If we've got the same mass for each one and we change the volume, that will change the density. So if we increase the volume, like going to a liquid expansion, gas severe expansion, we get a decrease in density. So if the density decreases the other direction, that means from 4 degrees to 0 degrees, the volume has to increase again. So this is a maximum density, minimum volume. Now that's unusual for most substances. Most substances follow the trend. Density decreases from the solid to the gas. Water's different. And the reason it's different is the crystal structure of ice. Okay. Have I talked about this before? Okay, I'll do it again. When water forms a solid, when it turns to ice, you can see evidence of this in snowflakes. Right? You ever catch a snowflake and look at what's its shape? It's a hexagon, right? When water forms a solid, it arranges itself into this crystal structure that is in a hexagonal form, like this. So this would be like, I don't know, oxygen here, hydrogen, oxygen, have another hydrogen there, another hydrogen there, and then maybe an oxygen here. This is a hydrogen, and another hydrogen there. So these bonds here would be those intermolecular forces. This is a molecule. This is a hydrogen. So there, and I messed up the. This is water molecule. This is the water molecule, and this, there we go. And then that one and this one should be intermolecular. Okay, so water arranges itself in that regular structure. And what happens is rather than the molecules just being sliding past one another, they have to expand to make room for this empty space. And that's what increases the volume of water and decreases its density. And that's a good thing. Like, what would happen if water followed the trend for all solid liquid gas transitions? Well, if it got cold enough outside for the lake or the ocean to freeze on the top, what would happen? Sink to the bottom. Freeze some more, sink to the bottom. Pretty soon, every ocean, lake, and river on planet Earth would be solid ice. Right. But since the solid is less dense than liquid water, it floats and forms that skin across the top, insulating the rest of the body of water underneath, so the animals don't get frozen to death. Okay. Oh, here we go. More detail. The that arrow that I used for let's see, to show the dipole here, like that toward oxygen, that's called the dipole moment. And moment is a term that physicists use to designate a vector quantity of force. Okay, so it's not only the amount, there's Madison, it's not only the magnitude of the force, but the direction of the force is important. So if the molecules have this dipole moment, they can attract one another. That's purely electrostatic attraction. And rule of thumb, on average, the force of attraction between two dipoles is about 1% as strong as a covalent bond. Now, it might be a little stronger for hydrogen bonding, right? Because there's a range in there. And then you can also get, I left this one out. If you dissolve an ionic substance in a molecular substance like salt in water, then the salt is going to break apart into ions like that. And when that happens, you get an ion dipole interaction. Okay. And then, of course, if it's the anion would be like this. Excuse me. It's not right. This. Because this is positive, and you get that attraction. Hydrogen bonding is just like I said, nitrogen, oxygen, fluorine, and hydrogen. So you have to have hydrogen there. And then the London dispersion forces are very, very weak. But all molecules have them. The melting and boiling points are physical properties of any substance that relate to the strength of these intermolecular forces. The higher the intermolecular force, the higher the boiling point and the higher the melting point. They are parallel. In other words, they're proportional to one another. Increase the forces, increase the melting and boiling points. Here's what I was talking about earlier. When we compare, we can look at this in two ways. The first, let's look at period 2, across the x-axis, period 2. So you have hydrides, excuse me. No, sorry. Let's look at the top line, I guess call that gold color. If you start with tellurium hydride, then its boiling point is just under 0 degrees. Then if you go down to selenium hydride, your boiling point decreases. And hydrogen sulfide, boiling point decreases again. So if we follow the trend, Water should have a boiling point at around minus 80 degrees. Instead, with hydrogen bonding, is 100 degrees. Now, the reason you get the trend for these others is they don't have the opportunity or the strength of dipole moments. So what we're looking at is London dispersion forces for the tellurium hydride, selenium hydride, and hydrogen sulfide. So the larger tellurium gives you the London dispersion forces that you need to hold it together. Whereas selenium is a smaller atom and sulfur is even smaller than that, so their London dispersion forces are decreased. But when we get to water, dihydrogen oxide, you're talking about hydrogen bonding because of the strength of the oxygen atom, the electronegativity of oxygen increases significantly. And you see that trend with also hydrogen fluoride and its neighbors in its group. And look at nitrogen also, right? Nitrogen should be decreased further, but it has hydrogen bonding. But when you get to the carbon group, you get the trend continues because carbon is not electronegative enough to induce hydrogen bonding. So when we go from selenium to germanium to silicon to carbon, the trend continues. Okay, that's the whole point of this graph, is to point out the effectiveness of hydrogen bonding in breaking the trends. Okay. Which one of these molecules is capable of forming stronger intermolecular forces? Well, obviously water. Because it can form hydrogen bonding, whereas nitrogen only has access to London dispersion forces. Okay. Here's an example where we have a formula, a molecular formula with two different structures, C2H6, H6O. You can get two different structures out of this. You can get you can get ethanol, or you can get dimethyl ether. Okay. And even though they have the same molecular formulas, they have radically different boiling points, right? Because you have access here to hydrogen bonding, which would increase the boiling point. Whereas here you have a perfect balance around that oxygen and you don't have a dipole. And obviously you don't have hydrogen bonding either because there are no hydrogens attached to that oxygen. Which one of these gases would behave more ideally at same conditions of pressure and temperature? Remember what ideal gas means, right? It means that the gas stays a gas all the way down to absolute zero. There are no intermolecular forces or weaker intermolecular forces. So, and the ideal behavior for all gases, if you want to impose ideal behavior, is high temperature and low pressure. So in those circumstances, which one of these would be more ideal? As you decrease the temperature, which one's going to condense first? Carbon monoxide, right? Because nitrogen has no dipole, right? It only has London dispersion, whereas carbon monoxide has a dipole. That. So this one's going to behave more ideally. That just means that it doesn't interact with its neighbors much. Okay, what do we know about liquids? Well, they can't hold their shape. They need a container. But that's how they're different from solids. They can maintain their volume just like a solid can. But, and that also depends on pressure. Solids are absolutely incompressible. But liquids do exhibit some compressibility because you have some added space between the molecules so they can move. But if you put enough pressure on them, you can get them closer together. We know that's true from laboratory experiments, but in nature, we've been able to sample the density of water at 2 miles down under enormous pressure. And the density of water that deep is greater than it is at the surface. Taking all other factors into consideration, like salinity, right? We know that high salinity means high density. So if you go to the Great Salt Lake or the Dead Sea, they say you can float with about that much of your body in the water. Whereas with fresh water, you'll sink till about right here. Okay, they're not rigid. Compared to gases, they have high density, just like solids. They have this unique quality called surface tension. And surface tension simply means that there's a force holding the water together stronger at the surface than in the rest of the volume. And it's a resistance of the liquid to increase its surface area. So surface tension is responsible for spherical droplets of water. Of course, if you can see slow motion film or stop motion film of rainwater, you'll see rather than a sphere, you'll see what? Kind of a teardrop, right? Yeah. That's due to atmospheric drag. The air drags on it and pulls it out like that. But if there were no air, then you would get perfectly spherical droplet. And that's because this minimizes surface area. The sphere is the smallest for any volume. The sphere is the smallest volume, surface area to volume ratio. The smallest surface area you can get for any volume is a sphere. So that's why wild animals in northern climates or extreme southern climates look kind of roundish, chubby-like. And they're large because that minimizes area to volume ratio. And that's good, so you don't lose so much heat to the cold. Liquids with large intermolecular forces tend to have high surface tension. Okay, have you ever seen, well, I've seen them eyeball to eyeball, but have you ever seen films of what these insects, they call them water skimmers. Have you ever seen those? They're insects, so they have 6 walking legs, and they're sitting right on top of the water, right? And their feet are spread way out to distribute their weight over a larger area. And at where their feet touch the water, you'll see a depression. So what they're doing is they're taking advantage of surface tension to hold themselves up. Now, do I have a slide explaining what surface tension is due to? Let me see. I don't want to steal my own thunder. Okay. I'll draw you a picture. When you have a liquid, any liquid, in your container, right, and you have molecules throughout the liquid, You also have molecules right at the surface. They have a certain attraction for their neighbors. Here, in the thing, of course, in 3 dimensions, you have those forces distributed in 3 dimensions. But at the surface, you're missing this component right here. Right? So those forces are redistributed to the neighbors next to each other. So the forces at the surface of the liquid are stronger than they are in the body of the liquid. That's where the surface tension comes from. Now, if we have depending on the intermolecular forces, you can have higher surface tension for some liquids than others. Water has a certain surface tension. Mercury, which is a metal, obviously, has a much, much higher surface tension than water does. So it would be simple for me to walk across a pool of mercury. Barefoot, of course. There's also another effect that you'll see in liquids, and that's capillary action. Everybody know what a capillary is? It's a very thin tube. Right? So let's say we have 2 tubes. Let's draw a big one here, like that. 2 tubes, and we submerge them in liquid. Okay. Now, there are 2 types of forces involved here. Right? Within the liquid, there are cohesive forces. That is, those forces that are drawing those molecules together. We know that's true because it's a liquid. Right? There have to be a certain amount of force imposed upon each molecule in order to keep them in that liquid state. But if we insert a tube here, then now we're introducing adhesive forces. That is, forces between the molecules of the liquid and the tube itself. Okay, so there's a battle going on between those 2 forces. If the let's see. Okay, that's an explanation for that. The capillary action itself is an observed rise in the level of the liquid in the capillary as opposed to outside the capillary. Now, if it's wide like this, you're not going to see anything. It's just going to sit right there. But with a narrow tube, it might move up some, like that. What you're witnessing there is a battle between cohesive and adhesive forces. So if we take that capillary and let's blow it up, so the liquid's here. First thing that's going to happen is, if you've got a liquid level here, there are going to be cohesive forces drawing that liquid to the surface of the capillary tube. Okay, and this is especially true if it's glass, because glass is made of primarily of silicon dioxide. It's got those oxygens sitting out there with their negative charges. And they're going to be pulling on, say this is water, they're going to be pulling on the positives of water. Right? So you get cohesive, and it starts to creep up the walls. Right? Creep up the walls like this. When it does that, the adhesive forces tend, especially at the surface, tend to pull, and they'll walk the level of the water up. And then the cohesive forces take over again. Now, these are all happening at the same time, but I'm breaking them down into separate forces so that we can talk about what happens to get the water to move up. So each time this happens, you get cohesive forces and adhesive forces acting against one another. Now, when does it stop? It stops when gravity takes over. when the mass of water that's moved up in the capillary balances the forces that are trying to draw the water together and hold it against the surface of the capillary. Okay. So with a thin capillary, the water is going to move really high because of the cylinder, right? The volume of the cylinder is area times height. So if we decrease the area, then the height can get longer for the same volume and mass of water. Okay. That's capillary action. We can see whether the cohesive forces are winning versus the adhesive forces. All right, if we get a rise of the liquid here, that means the cohesive forces are initially stronger. The adhesive forces are stronger than the cohesive forces. So they tend to draw the liquid up the tube. But if the cohesive forces are much, much stronger than the adhesive forces, then you see that in not a convex meniscus, but you see it in a concave meniscus. That says the cohesive forces are much stronger than the adhesive forces because the surface tension is trying to draw that into a sphere. And since there's so much weight below here, the only part of the sphere it can get is right here on top. That's mercury. Mercury is a perfect example. If you've ever seen a mercury barometer, you look at the barometer, the meniscus is convex. And in fact, when you read a barometer, you read at the top of the meniscus. If you read glassware that's calibrated for aqueous solutions, you read that at the bottom of the meniscus. Okay, cohesive forces dominate if you have a convex meniscus. Concave meniscus, the adhesive forces dominate until mass breaks the tie. Okay, another characteristic of liquids is viscosity. What do we mean by viscosity? We say something is viscous, we're saying it's thick. Kind of like molasses in winter. Or Heinz ketchup. Right. They have commercials, old commercials. You just turn the bottle upside down in the commercial and they're waiting for it to come out. It's very viscous. It simply means that there is a resistance to liquid flow. Actually, this is true for liquids. Gases have viscosity too, only it's much, much lower than liquids, but they still have a viscosity. Some liquids flow, some gases flow more easily than others. But we're going to confine our discussion here to liquids for the near term. Liquids with large intermolecular forces tend to be highly viscous. Or molecular complexity. What do we mean by molecular complexity? Well, big molecules. Big molecules have the opportunity to intertwine with one another, and that makes them more viscous. Now, the viscosity tends to increase if you increase the concentration. If you're dissolving something in the liquid, say sugar, the more sugar you put in water, the thicker it gets. Until you get something like honey, right? Honey is very high concentration of what we call invert sugar. It's sucrose that's been split into glucose and fructose. That's what bees do when they harvest sucrose from flowers, take it back to the hive, and they dip their head into the cell and they regurgitate the sugar, and then they spit. They spit an enzyme in there that breaks the sugar apart into two molecules, glucose and fructose. rather than sucrose. Sucrose is both of those combined together. And when you do that, split them apart, you increase the availability of hydrogen bonding for those sugars. We'll talk about, at some point in the future, we'll talk about the osmotic pressure based upon, in fact, I think it's in, is it this chapter or next chapter? I think it's next chapter. So keep that in mind. You increase the concentration of sugar or any solute in a liquid, you increase its osmotic pressure, and that's why honey is shelf stable. You don't have to put honey in the refrigerator to keep it from spoiling. Right? Its concentration is so high and the osmotic pressure is so high that microbes can't live in it. Right? They go in there and it just sucks all the water out of the cells. Okay. Solids, you can have two types of solids. We classify solids as either amorphous or crystalline. Amorphous solids have a disordered structure. A good example of that is glass. Glass is an amorphous solid. Typically, glass is. There are certain types of glass that are made with regular structure, but they're special cases. For the most part, glass is has disorder in its crystalline structure. That's kind of a contradiction. In fact, there's one line of thought among some scientists that glass is not a solid, but a supercooled liquid. Who knows? Well, we know that rock can be deformed, right? Deep in the earth under certain pressure. Enormous pressure can deform rock. So I guess a solid can be malleable. But crystalline solids have an ordered structure. And we can define that in terms of unit cells. That is, a unit cell is that part of the crystal that is repeated throughout the structure. This is the smallest three-dimensional repeating unit in a crystal, the unit cell. There's also another way to describe crystalline solids. It's called the closest packing structure. Now, you can describe a crystalline solid in either of these ways or both of them. But the physical arrangement of atoms and molecules in a crystalline solid is just there. That is, right? Nature just does what it does, and we try to explain it. These are two ways of explaining crystalline solids, the unit cell and the closest packing structure. It depends on which one you have, which solid you're describing, as to which one works best. But each has its advantages. Yeah, it's like two sides of the same coin. Okay, unit cells. There are a whole host of different possibilities, but most solids fall into one of these three unit cell categories. This doesn't cover all of them, and we can't do that because this course, I mean, we've only got a certain amount of time we have to spend on this topic. The simplest unit cell is the simple cubic. And that would simply be, we draw our cube just like we used to in grade school. There's our cube. And we're going to keep it really simple. We're going to say we're going to stick to atoms, just individual atoms, and we can expand upon that later. But if you have an atom at each corner of this cube, that gives you a simple cubic unit cell. Now, this is the easiest way to describe it, but in fact, the space filling model shows us what's actually happening. In the space filling model, these guys are big enough to touch each other on edges. They should be touching. So if you wanted to know the size of that cube, say you want to know the volume of that unit cell, right? How do you tell the volume of a cube? You just need the length of that side, right? So if this is A, the length of that side, A cubed equals the volume of that unit cell. That's easy, simple. Another possibility is if we have that cube and we have atoms at each of the corners again, but now we have another atom right in the center. Okay, this is simple cube. This is body centered. Cube. Okay, and notice what happens with the space filling model. When you stick something in the center, now these guys on the edge can't touch each other. Okay. Over here, we could say A is actually equal to this radius plus that radius, or if they're all the same atom, it's just the diameter of the atom. The diameter of the atom cubed would be the volume. But in this one, they don't touch. They only go about that far. And then this one in the center keeps them from touching. So determining the edge of that cube is an exercise in geometry. And I had a handout, but I didn't put it out because I didn't know if anybody would be interested in it. That describes, that describes how to determine the length of a body-centered cubic unit cell. I'll leave it here if you want that. If you're interested in geometry, that'll do it. The other possibility is if we have our cube and we have an atom at each corner, and we also have an atom on each face. The face-centered cubic. How many should I have? I should have 1, 2, 3, 4, 5, 6. 1, 2, 3, 5. I'm missing one somewhere. That one's centered. Face, face, face. There's face. There's front face. There's a face down here also. 1, 2, 3, 4, 5. And then top 6. Oh, that was right. Okay, so we have 6 atoms on the face of the cube, and we have an atom at each corner of the cube. This is a face-centered. Cubic. Unit cell. Is this going to be a video? I think it's a video.
If you could travel within a crystalline solid, you would see the particles, atoms, ions, or molecules arranged in a regular array. Here, the spaces are greatly exaggerated, but in reality, the particles are packed close together. The unit cell of a crystal structure is the smallest portion that defines the structure. Stacking unit cells next to each other in all 3 directions gives the structure. Many elements and simple compounds have unit cells from the cubic crystal system. Let's examine the 3 types of cubic unit cells. All cubic unit cells have particles at the corners of a cube. The simple or primitive cubic unit cell has particles at the corners only. In reality, the particles lie as close to each other as possible. Note that the particles touch along the cube edges, but not along a diagonal in the face or along a diagonal through the body. By slicing away parts that belong to neighboring unit cells, we see that the actual unit cell consists of portions of the particles. When the cells pack next to each other in all three dimensions, we obtain the crystal. If we fade the others out, you can see the original group of 8 particles within the array and the unit cell within that group. We find the number of particles in one unit cell by combining all the particles' portions. In the simple cubic unit cell, 8 corners, each of which is 1/8 of a particle, combine to give 1 particle. A key feature of a crystal structure is its coordination number, the number of the nearest neighbors surrounding each particle. In a simple cubic array, any given particle has a neighboring particle above, below, to the right, to the left, in front, and in back of it for a total of 6 nearest neighbors. The body-centered cubic unit cell has a particle at each corner and one in the center, which is colored pink to make it easier to see. With full-size spheres, you can see that the particles don't touch along the edges of the cube, but each corner particle does touch the one in the center. The actual unit cell consists of portions of the corner particles and the whole one in the center. 8/8 give 1 particle, and the one in the center gives another for a total of 2 particles. In this tiny portion of a body-centered cubic array, you can see that any given particle has 4 nearest neighbors above and 4 below for a total of 8 nearest neighbors. The face-centered cubic unit cell has a particle at each corner and in each face, which are colored yellow here, but none in the center. The corner particles don't touch each other, but each corner does touch a particle in the face, and those in the faces touch each other as well. The actual unit cell consists of portions of particles at the corners and in the faces. 8/8 at the corners gives 1 particle, and half a particle in each of 6 faces gives 3 more, for a total of 4 particles. In this tiny portion of a face-centered cubic array, notice that a given particle has 4 nearest neighbors around it, 4 more above and 4 more below for a total of 12 nearest neighbors. Stacking spheres shows how the 3 cubic unit cells arise. Arrange a layer of spheres in horizontal and vertical rows. Note the large diamond-shaped space among the particles. Placing the next layer directly over the first gives a structure based on the simple cubic unit cell. Those larger spaces mean an inefficient use of space. In fact, only 52% of the available volume is actually occupied by spheres. Because of this inefficiency, the simple cubic unit cell is seen rarely in nature. A more efficient stacking occurs if we place the second layer over the spaces formed by the first layer, and the third layer over the spaces formed by the second. That simple change leads to 68% of the available volume occupied by the spheres and a structure based on the body-centered cubic unit cell. Many metals, including all the alkali metals, adopt this arrangement. For the most efficient stacking, shift every other row in the first layer so the large diamond-shaped spaces become smaller triangular spaces, and place the second layer over them. Then the third layer goes over the holes visible through the first and second layers. In this arrangement, called cubic closest packing, spheres occupy 74% of the volume. Note that it is based on the face-centered cubic unit cell. Many elements, covalent compounds, and, as you'll see in the next 2 examples, ionic compounds adopt cubic closest packing. Sodium chloride adopts the sodium chloride or rock salt structure, as do many other alkali, halides, alkaline earth oxides and sulfides, and other ionic compounds. Picture separate face-centered cubic arrays of chloride ions and sodium ions as they approach and interpenetrate each other. The smaller sodium ions fit in the holes between the larger chloride ions and the NaCl unit cell. Zinc sulfide adopts the zinc blend structure, as do the copper-1 halides and several other compounds. If face-centered cubic arrays of zinc ions and sulfide ions approach and interpenetrate slightly offset from each other, each ion becomes surrounded tetrahedrally by 4 of the other ions. Note the blinking zinc ion and the 4 sulfides. You can see the relative positions in this slightly expanded view of the zinc blend unit cell.
Okay, that was probably more than you wanted to see in one sitting. It takes a three-dimensional eye to pick up on the situation. Here, what we've close to the end of that video, we saw the author, the narrator, was drawing a parallel between the face-centered cubic and the cubic closest packing. This is the closest packing model that has parallel in face-centered cubic. Those two different ways of, go backwards, two different ways of describing the system. So closest packing structure doesn't always fit with the unit cell idea, but we did learn that simple cubic is very rare, whereas body-centered and face-centered cubic are much more common. Okay. Now I'm going to bore you with some math. Actually, I think it was a father and son team. Their Bragg was their last name. And they were interested in determining what is the distance between atomic centers in a crystal structure. And what they hit upon was the fact that if the wavelength were short enough, say in the X-ray range, then they could treat the packing of atoms as if they were reflectors. They were diffractors. So Bragg's equation was developed from that. In this formula, N times lambda is equal to 2, it's a proportionality constant. And D is the distance between layers. And theta is the angle of attack. So you're shining your X-rays at a given angle, rather this angle, that angle, that angle. And then the distance between the layers in that closest packing model, think of it in those terms. And then this lambda is the wavelength of the light, usually X-ray. And then N is the order. It's an integer, but it references the order. So you can shine the X-ray. Let me give you a practical example. When I was working on my PhD in soil science, I collected soil samples from my research plot, and soils, to make a long story short, soils can have different size particles in them. Right? They can have sand size particles, they can have silt size, which is smaller, and they can have clay size particles. When you get down to the clays, you're getting to the point where you get chemical reactions occurring in the soil. That's where the action is. So I separated out the clays from my soil, and I wanted to know what type of clay is it. So once I got the clay separated by tedious methodology and in a suspension of a drop, then I put a drop on a glass slide and then let it dry. And as it dried, the clay particles are like plates. So they lay down like this on one another, just flat plates. Then I put it in the X-ray diffraction machine and I ran a scan. And then what it would do is a given wavelength was tunable, but I used a particular wavelength, and then I scanned it through different angles. And as I scan through angles, the detector on the other side would pick up the intensity of the reflected energy. And if it got a peak of energy, that means I was at an angle for one of these orders, like first order, and then keep going, second order, third order, so forth. And once you plug that number in, of course, for first order is going to be the strongest signal, so we tended to use that one. 1 here times the wavelength equals 2 times this unknown, and then the angle that we got. So that told me I could solve for the distance between the layers in that crystal structure. Oh, this is what we're talking about. This is a representation of what's happening when the light strikes that crystal. You get incident rays and reflected rays, and at a certain angle, you get constructive interference because some of the light rays are bouncing off the second layer and the third layer and the fourth layer. And if they happen at just the right angle, then they will be constructively, they will reinforce their signal. All right, that's the theoretical basis for the Bragg equation. Now that's for 2 dimensions. You can also get X-ray diffraction in 3 dimensions, only it's a little more difficult to interpret the spectrum. If we do that through a crystalline solid, then you get this a 2-dimensional picture. And that's how many, most, in fact, crystals are, the structures are determined. This is the way that the structure of DNA was teased. The real problem with DNA was not just the interpretation of the spectrum. The real problem with DNA was to get it into a crystal structure, because DNA is a really long molecule and it tends to be like this. So you want to get it into a regular crystal structure so that when you shine this X-ray on it, it will behave like a crystal and not like an amorphous solid, because amorphous solids won't give you any information. So, and I forget the lady's name. I wonder if I've got it here somewhere. No, I don't. The woman who was a lab assistant, worked for Watson and Crick in England, who actually did the X-ray diffractions, worked out the preparation of the sample so that you could get this crystal structure. And I'm sure Watson and Crick had something to do with it, suggestions and so forth. They got the Nobel Prizes. She didn't get a Nobel Prize, but by the time that the prize was awarded, she had passed away, I think, from breast cancer. But this pattern on the photographic plate, and now I'm sure we have solid state detectors do it for us, is characteristic of certain types of crystal structure. Okay, another way of looking at crystalline solids, you have the possible ionic solids, and the simplest description of an ionic solid for me would come from sodium chloride. You have sodium ions and chloride ions in this regular structure, and you know the unit cell dimensions and morphology because you can see the gross structure of the sodium chloride crystal. All you have to do is spill some on the table and look at it with a magnifying glass. You see little cubes. So you get this cubic structure for some ionic solids. Others are different. And they will always have this regular crystalline structure of some kind. Molecular solids, on the other hand, have covalently bound molecules at each of the lattice points in the structure. So for water, for instance, its structure is that hexagonal form, and it propagates in all directions. But each of the points of the hexagon are occupied by molecules. Then you have atomic solids, and that's where I was focusing our attention here, with atoms, just neutral atoms from the periodic table. Okay, so what do we have here? Well, on the left, we have diamond, right? It has a tetrahedral arrangement of covalently bound carbon atoms. And in fact, if there are no flaws in the diamond, and you were small enough, you could stand on one of those carbon atoms, jump to the next one, and keep going from one side to the other, and there would never be a break. It's just one huge molecule. All right. So this is a covalent solid, diamond. This is an ionic solid with sodium and chloride in that structure. And molecular is a hydrogen bonding, holding those water molecules together in their lattice structure, hexagonal structure. And this is just a table out of your textbook that combines everything together. We've looked at ionic solids, molecular solids, and the atomic solids can be broken into 3 separate groups. And the forces that hold them together, these metallic atomic solids are held together by delocalized covalent bonds. Another name for that is the metallic bond. And we're not going to spend a lot of time on that one, the bond itself. The nonmetals, the networks are directional covalents. They lead to giant molecules like diamond. And then the London dispersion forces are responsible for solids formed from the noble gases. Okay, now we're gonna transition from the unit cell to closest packing model. For the closest packing model, we assume that and we're going to stick to metals now for simplicity's sake. The metal atoms are uniform hard spheres. All right, we just assume that. We know they're not, but to simplify the description, we're treating them as if they were solid spheres, like marbles. And they're packed in layers. I've got a video coming up in a second. Yeah. Okay, this video is very good description of the closest packing model, but you have to tune your ear to an Indian accent. Okay.
The three-dimensional modes of packing can be easily understood by dividing the whole process into 3 steps. Close packing of spheres in one dimension. In one-dimension close packing, there is just one way of arranging the spheres. Here, the spheres are arranged in a row touching one another. As a result, each sphere is in contact with 2 neighboring spheres. Thus, in one-dimensional close packing, the coordination number is 2. Close packing of spheres in 2 dimension. Close packing structures in 2 dimension can be generated by stacking rows of one-dimensionally closed packed spheres, one above the other. This can be done in 2 ways: square close packing and hexagonal close packing. Square close packing. In this type of packing, the second row of spheres is placed in contact with first row in such a way that the spheres of the second row are placed exactly above the spheres of first row. In such an arrangement, the spheres are aligned horizontally and vertically such that each sphere is in contact with 4 other spheres. So, the coordination number is 4. If we call the first row as A-type row, the second row being exactly same as the first row, so it is also called as A-type. If we keep on placing such similar rows one above the other, then such an arrangement is known as AAA type of arrangement or square packing. Hexagonal close packing. In this type of packing of spheres, the second row of spheres is placed in a staggered manner such that the spheres fit in the depressions of the first row. If we call the first row as A-type, then as the second row is different from the first row, it can be called as B-type. Now, if we place a third row above the second row in the similar manner, we will observe that the third row spheres are aligned with those of first layer, and each sphere is in contact with 6 other spheres. So, the coordination number is 6. Similarly, on placing the fourth layer, we will observe that the fourth row of spheres are aligned with those of second layer. Hence, this type of arrangement is known as ABAB type of arrangement or hexagonal close packing. If we compare square close packing with hexagonal close packing, we will observe that empty spaces are less in hexagonal close packing than compared to square close packing. Now, what are these empty spaces and what role do they play in packing efficiency? The empty spaces in between the spheres are known as voids. These voids are responsible for decrease in packing efficiency of the solid crystal. More the number of voids, less is the packing efficiency of the crystal. Now, you must be wondering what is meant by packing efficiency. We have discussed about this in later part of the section. Now let us study about close packing in 3 dimension. 3-dimensional close packing from 2-dimensional square close packed layers. This type of packing is obtained by placing 2-dimensional square closed packed layer above the first one, such that the spheres of the second layer are exactly above the spheres of the first layer. In this arrangement, the spheres of both the layers are perfectly aligned horizontally and vertically. On arranging layers one after the other in this pattern, we will observe that each sphere is in contact with 6 other spheres. 4 from the same layer, 1 from the layer above, and 1 from the layer below that sphere. So, the coordination number is 6. If we call the first layer as A-type, and since all the layers are also of the same type, this kind of arrangement is known as AAA type of arrangement. On observing carefully, we will find that this arrangement has generated a simple cubic lattice and its unit cell is primitive cubic unit cell. Dimensional close packing from 2-dimensional hexagonal closed pack layers. The 3-dimensional hexagonal closed pack structure can be obtained by placing 2-dimensional hexagonal structures one layer above the other. Placing second layer over the first layer. Let us take a two-dimensional hexagonal closed-packed layer A. Notice this layer has triangular voids. Place a similar closed-packed layer in such a way that the spheres of the second layer are placed in depressions of the first layer. As the spheres of the second layer are aligned differently as compared to the first layer, so let us call this layer as B-type. On observing, we will notice that not all the triangular voids of the first layer are covered by the spheres of the second layer. This gives rise to a different arrangement and different voids. Voids. There are two types of voids: tetrahedron voids, denoted by T, octahedron voids, denoted by O. Let us study how these voids are formed. When we place a closed packed layer above the depressions of the first layer, we will notice that at some places the triangular voids of the first layer are being covered by the spheres of second layer. At such places, a type of void is formed. This type of void is known as tetrahedral void, T, since a tetrahedron is formed by joining the centers of the four surrounding spheres. While at other places, we will notice that the triangular voids of the first layer coincides with the triangular voids of the second layer, such that their triangular shapes do not overlap. At such places, another type of void is formed. This type of void is known as octahedral void, O, since an octahedron is formed by joining the centers of the six surrounding spheres. Now, in case we need to calculate the number of tetrahedral and octahedral voids in a crystal structure, then just knowing the number of spheres will serve the purpose. Suppose there are n spheres in the crystal structure, then the number of octahedral voids generated is equal to n. The number of tetrahedral voids generated is equal to 2n. Placing third layer over second layer. Now let us place third layer over second layer. Stacking of third layer over second layer can be done in two ways. First, by covering tetrahedral voids. Second, by covering octahedral voids. By covering tetrahedral voids. The tetrahedral voids of the second layer can be covered by placing the spheres of the third layer over them. On doing so, the spheres of the third layer will get exactly aligned with the spheres of the first layer. So, if we can call the first layer as A-type and the second layer as B-type, then the third layer will also be A-type. As the pattern of spheres is repeated alternately in other layers, so this pattern is known as AB-AB pattern, and the structure formed is known as hexagonal close-packed HCP structure. In this type of structure, each sphere is in contact with 12 other spheres, 6 from the same layer, 3 from the bottom layer, and 3 from the top layer. So the coordination number is 12. Covering octahedral voids. The octahedral voids of the second layer can be covered by placing the spheres of the third layer over them. On doing so, the spheres of the third layer are not aligned with the spheres of either first layer or second layer. So, if we call the first layer as A type and the second layer as B type, then this third layer will be C type. Now, if we place the fourth layer over the octahedral voids of the third layer, then the sphere gets aligned with the spheres of the first layer. Thus, this pattern is known as ABC type, and the structure formed is known as cubic close-packed CCP or face-centered cubic FCC structure. In this type of structure, each sphere is in contact with 12 other spheres, 6 from the same layer, 3 from the bottom layer, and 3 from the top layer. So, the coordination number is 12.
Okay, that was a long one. Give you time to adjust your ear to her accent. Okay, I tried to fill in what we knew from the unit cells to the closest packing model, and I missed one. Let's see, cubic hexagonal closest packing. That's the one I'm missing. I think it fits in here somewhere, but I'm not so sure that it is related to the face centered. That's the issue in my mind. So the AB packing, the second layer is like the first layer, but it's displaced so that each of the second layer occupies a dimple in the first layer. That dimple gives it the tetrahedral void. Okay. So if you connect the centers of all the touching spheres, you get a perfect tetrahedron. And that's the ABAB. Where'd it go? Oh, that's the one I couldn't find up here. That's hexagonal closest packing, or HCP. Hexagonal closest packing. And that has ABA structure with the tetrahedral voids. The ABCA is this one, where you cover the now that's okay. We have two possibilities, it looks like. Now this one, the no, cubic closest packing. All right, CCP. Yeah, there it is. Okay, no, that one's right. CCP, cubic closest packing. There you're covering the octahedral voids only. And that gives you a unit cell of a face-centered cube. This is very common. I think because it's most efficient for minimizing the void space. Let's see, hexagonal closest packing. Here we go. HCP. And that's a face-centered cubic too. Okay. So apparently this one could either be, and both of the coordination numbers are the same. Coordination number is 12 for both of them. It just depends on whether it's an ABA or an ABC. Cubic closest packing, here we go. Okay, that's an ABC. Yes, okay. And we can see with either one, you've got 12 closest neighbors, which is the coordination number. Now, I've already filled in the number of atoms in a unit cell, the number of spheres in a unit cell. I mean, if we've only got atoms, then that works. And how we count them. Since these unit cells have to share with their neighbors, right? They have to share with 1, 2, 3, 4, 5. Let's see, 1, 2, 3, 4, 5, 6. 6 neighbors. And if we share that atom with a cube here and here and here and here and here and here, we have to divide it into 8 pieces. So for the unit cell, we've got 1/8 of a sphere here and 1/8 for all these 8 pieces. So that's only 1 atom per unit cell, or 1 sphere per unit cell. All right. Oh, they're jumping all the way to that one. Okay, let's go to the body centered. You still got 1/8 for these, so that's 1, but this one belongs to that unit cell and that one only. So this one has 2 spheres per unit cell. And this one has half on each face, and there's 6 faces. So 6 divided by 2 is 3, plus a 1 for the corners, that's 4. So the face-centered cube should be 4. There's 6 times a half. There's 8 times an eighth. Add them together and you get 3 plus 1 equals 4. Okay. Simple cubic is 1 atom. Face-centered is 4. And I don't know if we've got the body-centered. Body-centered should be in there somewhere. It's not. Body-centered is 2. Okay. So what do we do with this information? Well, in order to calculate, say, the density of say, a metal that's in one of these 3 different types, we calculate the density based upon D equals mass divided by volume. So if we know if we can determine how many atoms are in each unit cell, then we can figure out what the mass of that metal is in the unit cell. Then all we need is the volume of the unit cell, and we can calculate its density. So for a simple cubic, of course, 2 times the radius of the atom is the side of the cube, and 2r cubed would give us the volume. Face-centered cube is a little different. Face-centered cube. So if we want to know this distance here, say this distance right here, then we need to know the radius of the atom, right? The radius here, and times the square root of 8. So r times the square root of 8 equals that side on that cube. Okay, I think that's in useful information too. In the back, if you look at the back of your review document, yeah, it should have those formulas. Okay, body centered cube of got. Well, memorize that one. This one's obvious. It's 2 times the radius of the atom is the side. And this one is square root of 8 times radius of the atom is the side. And this one I've got in there, you don't have to memorize. The next one is the body centered. Is 4 over square root of 3. So this one, A equals 4 over the square root of 3 times R. And Yeah, that's what this handout describes. It says, how do we get that number? And that should explain it to you if you're interested. Otherwise, it should be on the useful information. So this one, I don't know why I left that one off. That one right there, square root of 8. So now that we know how to find the volume of each of the cubes, then we can do a problem. Say we're given the silver metal crystallizes in a cubic close packing, which is a face-centered cube. And we're given the cell edge at 409 picometers. Right? We didn't have to use the radius of the silver atom to go the next step. So we're actually given A is 409 picometers. Calculate the density of the silver metal. All right. So in order to do that, I need more room. When you solve a problem like this, it's helpful to think backwards. If you want to know the density of the silver metal, how do we calculate density? Mass by volume. Okay, so we're going to have to determine the mass of silver in a unit cell, and we're going to have to tell the volume in that unit cell. So if we go for the mass in this face-centered cube, how many atoms do we have? We have 4 atoms per cube, right? Okay, so 4 atoms of silver per cube. Right? We want to know what's the mass of that cube. So the way to get it is to say what's the mass of an atom, right? And we need to know silver's molar mass is 107.87, and that's grams per mole. But we don't have moles yet, right? So if we have 6.022 times 10 to the 23rd atoms per mole, and now we got moles. And then we can multiply that with moles on the bottom, grams on the top, 107.87. 107.87 grams per mole, moles cancel. Now we have grams per cube. That fills in this part. Now we need the volume. 409 picometers. 409 picometers. Remember, for solids, the unit of measure is grams per cubic centimeter. So we need picometers in centimeters. Okay, so what's a picometer? Well, let's see. A nanometer is 10 to the minus 9th meters. A picometer is 10 to the minus 12th meters. So picometers, meters, 10 to the minus 12th, right? And then we can convert meters to centimeters. Right? We have 100 centimeters per meter. Right? So then meters cancel, picometers cancel, so we're left with centimeters. And then we just cube it. Okay, and that goes in here. So I think the animation is probably a little better organized. 4 silver atoms per unit cell. There. Okay. And the volume of the cell is, well, I went about it the other way here. We had cubic picometers, and then we changed it to cubic centimeters. But there's more than one way to get to the answer. And if we do those calculations, we should get 10.5 grams per cubic centimeter. And that is very, very close to the measured density of silver. Okay. Bonding models for metals. Right, we in the first semester, we stuck to ionic bonding and covalent bonding. But metals are little bit different. Historically speaking, metals used to be described in terms of the nucleus of the metal in a sea of electrons. That's why it's called the electron sea model. They just have all these electrons floating out there, and the nuclei of the metals were just pockmarked in there. Almost like the plum pudding model for the atom. But that didn't tell you anything about their energies, right? So that model didn't last very long, or the time it did last was doomed to failure eventually. So the molecular orbital model, which we've been introduced to already, can be applied also to metals. And for metals, we speak of it in terms of the band. And the illustrations coming up will explain that a little better. Remember, the more atoms you have, say if you only have two, then your molecular orbital model is kind of discrete energy levels, right? They're very far apart. But as you increase the numbers, say we went to 100 metal atoms, then the energy levels start to get closer together. And once you've got a chunk of metal, you're talking about moles. So the difference between the bands and energy bands in the molecular orbital model of a metal are very close together. And those electrons at the highest level are almost at infinity. They can be easily moved just by a little bit of energy. That's why metals are very good electrical conductors. You got those free electrons at the upper level, and they're very good conductors of heat. And since they can exchange electrons among the atoms, they tend to form very strong bonds as well. Okay, so this illustrates the molecular orbital energy levels for large number of atoms in a metal. And this is another illustration. The difference between let's see, I want to use the right terminology. The filled molecular orbital, or the highest occupied molecular orbital, or HOMO. The highest occupied molecular orbital and the lowest unoccupied, or the LUMO, are very narrow. In this case, they're saying 3s to 3p. So it's easy to add just a tiny amount of energy and get that electron up into the empty molecular orbital, and it can move either way, move to the next atom, and just keep moving. These are called bands. They're virtually continuous throughout the metal. Okay. All right, that's as far as we're going to go with explaining metal bonding. Now we're going to look at alloys. And alloys can be understood in terms of these regular crystal structures that we talked about before. There are two types of alloys. There's the substitutional alloy, and the interstitial. Remember what an alloy is. You have the largest amount of metal, and we substitute something in there. It's not pure anymore. And we change its physical properties by adding some other metal or some other non-metal, as a matter of fact. Right? If you substitute carbon in iron, carbon's a non-metal, in iron you get steel. Or sometimes you go too far and you get pig iron. But the substitutional alloy is one in which atoms of the metal are replaced by the alloying element. A good example of that is brass. Now you start with copper and you put some nickel in it and you get brass. So you can have brass fixtures on a Navy vessel that don't corrode very easily, or you can get brass in your musical instrument and you can hammer it out and make a trumpet or a saxophone or whatever. Interstitial alloys, on the other hand, retain all of the atoms of the original metal in their original position. And now the alloying element we substitute is so small that it fits in the voids. This is atoms of the metal are replaced, and this is alloying element fills the void. Not all of them, just some of them. Okay. So there's copper and zinc is not brass. What's copper and zinc? Bronze. Right. We've got a whole section of history named after that one, the Bronze Age. And the interstitial perfect example of that one is steel. Carbon is a very small atom and it fits in those voids of iron. And what it does is it prevents the shifting of layers. It locks them into place. That makes steel harder than iron. Pure iron, you can scratch it with your fingernail. Can't do that with steel. Okay, those were alloys. Network solids that we discussed earlier. These are allotropes. Allotropes of carbon are perfect examples of network solids. Diamond is still carbon. It's the element carbon, but it is formed by tetrahedral arrangements, covalently bound carbon atoms. Whereas graphite is a hexagonal structure of carbon atoms in layers. And they form, let's see, this. They form layers like this. It just goes on forever. But that's on in a two-dimensional layer. And then the only bonds that can hold them together are very weak between the layers. They would have to be, actually, they would have to be van der Waals forces, right? So what does that do? Well, as a practical matter, it lets those plates slide past one another very easily. That's why graphite is often used as a dry lubricant, because it's not wet, it doesn't absorb, it doesn't attract dust, yet it still provides that lubrication. We used to keep a can of graphite when I rode motorcycles, and it's got a long tube, thin tube, and you stick it in your cable guides, and you squirt that stuff in your cable guides, and keep your brake and your clutch cables moving easily. Okay. Here's a comparison of the alloys, the metals, pure metals, and the network solids. For diamond, you have a huge difference between the highest occupied molecular orbital, the HOMO, and the lowest unoccupied, the LUMO. There's a very big gap for diamond between the lowest unoccupied molecular orbital and the highest occupied one, or very big gap. Whereas with metals, we saw our previous example that the difference between these two is very narrow. So what that means is, for instance, thermal conductivity is very high in metals. They're very efficient conductors of heat, right? Whereas diamond is not. So if you take a stone to your local gemologist and ask them, is this really a diamond or is it fake? They have a device that they just touch it to the surface of the stone and see how fast the heat wicks away from their meter. If it's very slow, below a certain point, it's very good insulator, then they can confirm that it's a diamond. If it's something like a moissanite or a cubic zirconium, then it will have a much higher rate of thermal conductivity, and that meter will tell them. I don't know if I told you the story. A friend of my wife's wanted to give her a blue moissanite, right, as a gift. Only they were so stingy that we had to pay for shipping. So we paid, I don't know, $8 or something for shipping, and sent us a stone. And we took it to the mall. One day we were at the mall, and we had the stone with us, and we walked into Kay's, I think it was, and said, look at this beautiful blue moissanite. And they looked at each other and says, I don't think so. I think that's a diamond, a blue diamond. So they went and got their meter and put it on there. Sure enough, there's a diamond. Whoever sent that to us made a mistake. So we called them and said, go ahead and keep it. They were rich. So we immediately left the diamond with the jewelers and says, could you have your certified gemologist give us a certificate that that's what this is, so we can put it on our insurance. And we eventually had it mounted, set in a setting of some kind. Anyway, illustrated point. Graphite, on the other hand, has this layered effect, and you can see these layers. I think we talked about benzene at the end of the last semester, how it had the delocalized electron density would stabilize it. Well, the same effect is seen here in graphite. You get that delocalized electron density stabilizes the layers, but not between the layers, so they can move past one another. Ceramics. We're not going to spend a whole lot of time on ceramics. Ceramics is one of those terms. I had a professor, if I haven't told you this before, I had a set of procedures I was using to extract manganese from soils. And supposedly you would extract the most easily extractable manganese and then the more difficult ones as you go down with each step. And I said, how am I going to justify this to my committee when I go for defense? With theoretically, why am I doing it this way? And he says, oh, it's operationally defined, which means it's whatever you want it to be. So ceramics is another term that's operationally defined. We just say, this is what ceramics are. They have these common characteristics, and that's as far as we take the term ceramics. They're generally non-metallic materials. They're very strong, particularly in compression, right? Like concrete. Concrete is good in compression, but if you try to span between two pillars on a bridge and you have pure concrete, it's very limited in what it can support. So we add things like steel rebar in the middle, and that helps give it tensile strength as well. Or we shape it into I-beams, and that increases its strength. But typically, ceramics made from these non-metals are strong, but they're also brittle. They're very resistant to heat, and they're not easily corroded by most chemicals, like strong acids, bases, other aggressive chemicals. That's why certain types of ceramic bricks will be used in ovens, because they can stand the heat. They're typically made from naturally occurring materials like clays. You have clay deposits in certain parts of the world that lend themselves to certain types of ceramics better than others. Fine china is made from, in fact, I don't know where that comes from, but it's a special type of clay that's been deposited over time in veins, and you just dig it out and get it wet and form it into your plates and china utensils, and just fire it. Once you run it through the fire, it goes through a reaction called a pozzolanic reaction. It actually changes the crystal structure. Right. Okay, enough about ceramics. Semiconductors. How do we get semiconductors? Well, for the longest time, and before the age of electronics, we had two types of electrical materials, so to speak. We had conductors and non-conductors. That was it. So we put the wires in our wall with copper, and we insulated them with, we wrapped them with natural fibers to begin with and kept them separate. As if you look at pictures of old houses, they go up to the light bulbs. Rich people, they had two wires going up here with spacers to the light bulb. They never put them together because the insulation was not efficient. But once we got efficient insulations from polymers, plastics, then we could put them together in the same cord. Well, those are conductors. And the non-conductors were the insulated things that kept the crosstalk between the two conductors. Well, then it was discovered that you could create from conductive materials or non-conductive materials, you could create partial conductivity or semiconductors. And there are two types of semiconductors. You start with a material, and we generally choose silicon for two reasons. Silicon is right on the border between metals and nonmetals. So it's often considered a metalloid. Sometimes it acts like a metal, sometimes it acts like a nonmetal. But if we take the silicon in our structure, silicon, we have silicon, like we have silicon atoms, pure silicon. And if you've ever seen a pure silicon ingot, these semiconductor companies that make computer chips, they have to make pure, absolutely pure silicon, and they will grow it in liquid silicon. They melt it, and then they grow the crystal out of that silicon. And when it comes out, it's like this big around, and it's about 12, 14 feet long. And then they slice it. Well, it has to be pure, because what we're going to do next is called doping. We're going to dope that silicon with one of two types of atom. So when we do that, we replace that silicon atom, say this one, with say one that has more valence electrons than silicon. So go to the right, say phosphorus. Phosphorus now has, compared to the silicon around it, has an excess electron. That's an N-type or negative type semiconductor. Right? That electron can move with the proper impulse. Right? I mean, it's not a pure conductor, because once it gets over here, it kind of neutralizes it. It leaves a positive behind. But it allows for control. That's an N-type. When you dope it with something that has one or more valence electrons than the base material, in our case, silicon. Well, if you go to the left, say boron. So if you put boron in here, it's deficient. So now that's considered a p-type semiconductor. And when we move things in an n-type, we said to move the negative charge or the electrons. For the p-type, when we move a charge, we say we're moving the holes. Because we're missing an electron, we move that hole over here. Well, actually what happens is the electron moves that direction. But for convenience, we say the hole moves. The difference between the HOMO and the LUMO for a semiconductor, for the base crystal material like silicon, is not as big as a network solid like diamond, and it's not as small as metal, somewhere in between. So that gives us the ability to promote an electron up here or a hole up here. There are examples. Silicon with arsenic squared, is to the right of silicon. Right? It has one extra valence electron. So that's an N-type semiconductor. Boron, I've showed you before, is a P-type semiconductor. Oh, I thought I was close to the end. Well, that's okay. We got plenty of time. Let's see. Oh, we do have some more discussions. Okay. Can't relax yet. Ionic solids like sodium chloride typically have very, very high melting points because the bonds between them, those electrostatic attractions between the ions, are very strong. So you can get an ionic solid to melt, but it takes a lot of energy. Okay, the difference in the melting points depends on what are the attractive forces between the ions, the cations and the anions in the solid. And they're based upon two things. One is how big is the charge difference between the two, and what's the distance between the two. So if we are comparing two substances where the anions and the cations are exactly the same size, but one has a 2 plus 2 minus and the other has a 1 plus 1 minus, then the one with the more charge difference will be the stronger attraction and have the higher melting point. But typically what happens is not only the charge difference, but if you charge something like that, you get a difference in size too, and you allow the charges to move closer to each other. So the distance between them decreases, that increases the electrostatic attraction. So those two factors contribute to the not the intermolecular, but the interionic force of attraction. Okay. Okay. This is rehashing what we've looked at before. When you're looking at just a single layer, remember our Indian lady, she had the one-dimensional and then she had the two-dimensional. When you get the two-dimensional and you stagger the spheres so that they lay in the voids like this, then the void in here is a triangle, a trigonal hole. And this is only two dimensionals. If we then lay one on top to cover that hole, then we connect all the centers here and we get a tetrahedron. That's the tetrahedral void. or hole. If, on the other hand, let's see. That gives us the ABA. If we have the ABC and we only cover the octahedral holes, excuse me, we don't cover every hole, but we shift them so that they're like this, and then cover them with the next layer, and then the third layer, then we get an octahedral hole. Or a void, octahedral void. That's probably a more impressive word to use. So if we compare these three, actually, we're not comparing oranges and oranges, we're comparing apples and oranges, because the trigonal is a two-dimensional hole. The tetrahedral and the octahedral are three-dimensionals. If we go back and look at the arrangement, the octahedral hole is smaller than the tetrahedral hole. Excuse me, it's the other way around. Excuse me. The tetrahedral is smaller than the octahedral hole. And the trigonal, I don't know why I kept that in there, that slide, because trigonal is not 3 dimensions. Trigonal is 2 dimensions. So I would focus on octahedral has a bigger hole in it than the tetrahedral. Okay, and this came straight out of your book too, so I'm not going to spend time on this one. It just relates everything we've studied so far with properties, examples, and structural units. Now, we need to cover this topic because, let's see, we're going to need this. One second. No. Okay. For our lab, we're going to need chapter 11. So what does it look like when you enclose a liquid in a container and you cap it? Initially, you get some movement. Remember, in any substance at a given temperature, the temperature is a measure of the average kinetic energy. Temperature is proportional to the average kinetic energy of the molecules in that substance. Atoms, molecules, whatever. That means that there's a distribution of energies. So you get like a bell-shaped curve, sort of. And most of them are going to be with that kinetic energy. Some of them are going to have very high, some of them are going to have very low kinetic energy. These guys over here that have higher kinetic energy, they stand a better chance of actually leaving the surface from the liquid into the gas phase, and they do that. And they take some of that energy with them. So when they evaporate, unless you're maintaining and had the word in my brain, just flew right out. Unless you're maintaining the temperature, then the liquid will cool because some of that kinetic energy is being taken away. That's why when you come out of the pool on a hot summer day, you start to cool off, right? Because the water's evaporating from your skin and taking heat with it. So initially, it's all one way. Molecules moving into the gas phase. But eventually, you get to the place where you've got enough gas molecules or atoms in the headspace that some of them start to return, right? So you eventually reach a place where the rate of evaporation equals the rate of condensation. Okay. That's when you have physical equilibrium. Okay. And that concept of equilibrium is very important. It's all based upon rates. How fast is it happening? Because we're gonna take that concept and apply it to chemical reactions in the future. Okay. And this is just an illustration. Over time, the rate of condensation gradually increases from 0 to some value. The rate of evaporation generally stays the same. But once those rates are equal, then you have equilibrium. And on the macroscopic level, what you see is the volume of the liquid decrease to a certain point and then stop. No more. It's more evident when you've got a very volatile liquid like diethyl ether in there, and you can watch it go really fast. Now, once that equilibrium is established, we have what's called, we have a head pressure because it's sealed, and we can measure the pressure of the gas in that head space above atmospheric pressure. Well, actually, depending on how you do it, you can measure it below atmospheric too. But if we just plug it at atmospheric pressure, then the pressure will build above atmospheric to a certain point. And it depends on two things. It depends on temperature, because if you add more kinetic energy to that liquid, you're going to get more evaporation from the surface. And the nature of the molecules. If they have very, very low intermolecular attractions, holding the molecules together, then more of them will leave into the headspace and increase the vapor pressure. So this is one measured physical property of a liquid that is inversely proportional. As the intermolecular forces decrease, vapor pressure increases for any given temperature. So what's the vapor pressure of water at 100 degrees C? 1 atmosphere. Right. And we're assuming that we're saying, okay, the vapor pressure of water at 100 degrees is when it boils. And if it's boiling, that's 1 atmosphere pressure. That's kind of misleading, actually. This illustrates the vapor pressures of various substances. Water at standard temperature will give you a 24 torr vapor pressure. So the mercury column will be pushed down by that much pressure, right? In a vacuum, it goes to 760 torr at sea level. But if you put ethanol in there, the drinking alcohol, it will vaporize to a greater extent and produce more vapor pressure. So it's 65 torr at the same temperature. And then diethyl ether, which is what they used to use to anesthetize people before they operated on them, is extremely volatile. And it will produce a vapor pressure of 545 torr. Excuse me. Yeah, 2465. Yeah, 545 torr vapor pressure for diethyl ether. And I already told you this one. They're inversely proportional. Intermolecular forces and vapor pressure are inversely proportional. And as you increase temperature, you get an increase in vapor pressure. And the boiling point occurs at, well, the normal boiling point occurs at 1 atmosphere pressure. So the temperature at 1 atmosphere pressure at which the liquid boils is the normal boiling point. But boiling point could be anything depending on what the external pressure is. But the normal is 1 atmosphere. So for water, it's 100 degrees. For ethanol, it's 78.4. And for diethyl ether, it's 34.6. So if you dump some diethyl ether on your hand, it'll vaporize like that because your hand is, what, 37 degrees. I wouldn't want to do it, though. I'd rather put liquid nitrogen in my hand than diethyl ether. I'd be careful opening the can, too. Ethers tend to form peroxides, explosive peroxides. So if you got an old can of ether laying around and you look at the lid and it's got a crust, white crust around the lid, don't touch it. Very shock sensitive. It could blow up. Hopefully it's in a chemical cabinet. Easily, very slowly close the door and call for help. Okay. These two are related. The pressure, the vapor pressure, and the heat of vaporization, the delta H, the enthalpy of vaporization, are related by this equation. And this was proposed by, was it Clausius, Clapeyron? Yeah, I think it was. Both Clausius and Clapeyron proposed this. This is the very simple basic equation, and then we have to put it in some form that we can use. So if you know what the vapor pressure is, and you know what the temperature at that vapor pressure is, and you have this other constant, then you can calculate the heat of vaporization. But that's even, actually, this allows you to plot the log of vapor pressure equaling negative delta H of vaporization divided by R, the gas constant, plus, oh, wait a minute, 1 over T plus C. Notice this is Y equals mx plus B. This is M, this is X, this is Y-intercept. So if you measure the vapor pressure at different temperatures and then plot the log of the vapor pressure and the inverse of temperature, then you should get a straight, let's see it, straight line this way. And this slope is equal to negative delta H over R. That's a constant. So if you know the slope, all you have to do is multiply this side times R and change it to negative. And that's your delta H. Or you could take this approach and you could solve two simultaneous equations and come up with this ratio of vapor pressures at two temperatures and the two temperatures, and you can solve for delta H there without having to draw the graph. Oh, that temperature has to be in K also, because R has K units. All right, so that's the Clausius-Clapeyron equation. Let's see. Yeah, 1 over T2 minus 1 over T1. And we use the R value is the one with joules in it, not the liter atmospheres, because of this term. Heat is in joules. Okay, so here's an example. Vapor pressure of water at 25 is 23.8. Heat of vaporization of water is 25 degrees is 43.9. Calculate the vapor pressure of water at 65. In that case, we would just go, we would just go use this equation and find out what the vapor pressure is at unknown. Because we've got the delta H, we've got the two temperatures, we've got one of the vapor pressures, we only got one unknown. So we solve it for that one unknown. And it should be 194 torr. All right. Heating curve for water. This is a very simple physical state change as we add heat. As long as you've got a single phase, then the temperature is going to increase as you add heat. So ice is going to increase from, we're starting at minus 20, and as we add heat, we go up to 0 degrees. Now this is all at 1 atmosphere. So at this point, you have ice and water together. And as long as you have that, then the heat is not being channeled into increasing the kinetic energy, and as illustrated by the temperature, but we're increasing the kinetic energy so that we can send solid atoms into the liquid phase, or solid molecules into the liquid phase. So the temperature remains constant as long as you've got ice and water together. We're using energy now to break the bonds. And once you've got all water, then the temperature starts to rise again. As we're adding heat, we're adding kinetic energy to the individual molecules. Once we get to the boiling point, now we've got water and steam together, and the temperature levels off and stays there until we get all that water converted into steam. And then we superheat the steam. And many industries transfer heat from one place to another in their factories by these insulated pipes with pressurized steam. So there's a safety issue there. Right? If any one of them erupts, if it corrodes and breaks, then there are going to be some lawsuits from employees. Okay. So on a semi-quantitative level, which should we expect to be larger, the heat of vaporization or the heat of fusion? The heat of fusion is the heat required to melt a solid. Fusion is the other way, but the same heat is absorbed for the change to liquid as is given up by the change to solid. So which would be bigger, heat of vaporization or the heat of fusion? Huh? Oh, yeah. Yeah. A lot bigger. Because you're actually breaking the bonds. You're not even allowing the molecules to interact in any way. And that takes a lot of energy. Okay, phase diagram. So in a phase diagram, what we're doing is we're plotting pressure against temperature. So pressure is usually on the y-axis, and temperature here is on the x-axis. So as we, and there are some important parts of that diagram to take note of. They're listed here, but we're going to look at a diagram and show you. All right, so various parts of this graph are occupied by different phases. Right? Usually this is the solid part, this is the liquid part, and this is the gaseous part. Notice that the gas tends to form in low pressure, high temperature. Liquid is intermediate pressure and temperature, and solid tends to form at low temperature and high pressure. Okay, there's one point in here, say, we just make one up right there. And from this point, you can go here, you can go there, you can go there. Typically, for phase transitions for most materials, we'll go that direction with it. And this is the important one, the slope here. What these lines designate is on this line, anywhere at that pressure and that temperature, you will have both solid and liquid together. So our heating diagram shows us this somewhere along this line is where things flattened out temperature. And you have both phases together. Or on this one, you can have gas and liquid together at any point on that line. Or down here, you can have solid and gas together. So what does that mean? If the solid and gas, if you go across that line, you're either sublimating from solid to gas, or you're depositing from gas to solid. So you can hold the pressure constant and go this direction. You can hold the temperature constant and go that direction, or the other way, like that. And you've got sublimation or deposition. Okay, there's this special point right here. This combination of pressure and temperature for that substance is the triple point. And that's where solid, liquid, and gas are all together at the same, under these conditions, they're together in that container, all the three of them. Sometimes it's easy to see and sometimes it's not. Like you have an ice cube here and then water over it and then gas up here. This is a particular one for carbon dioxide. So let's see. Okay, so if we're going to do carbon dioxide, let's try to be consistent. That, and this one is kind of curved too. There's a point out here where now anything beyond this, pressure and temperature, is a critical point. So anything out here, this is the critical point. And what that means is that you still have a fluid, but you can't tell if it's a liquid or a gas. Okay. It's often called at this point, especially for CO2, is a super critical fluid. Industry uses supercritical fluids for extraction purposes. And in my former life, we had an instrument that sat on the floor about like this, and we had a tank of CO2 in the back, and we fed that CO2 into it, and it pressurized the CO2 to the point that we entered this part over here. And it had no, temperature's fine. Temperature's fine. We just pressurized it, and it became a supercritical fluid. Then we had our sample in the system, which had to be sealed, of course. A plant sample usually, and you introduce this supercritical fluid into that plant material, and it just went through it like hot knife through butter. Went through the cell walls in there, extracted whatever we wanted out of it, and then all we had to do was transfer that supercritical fluid extractant into another vessel and release the pressure. And the CO2 evaporated, and we were left with undamaged secondary metabolites. It was good for very sensitive molecules that didn't do well in heat type extractions, say with methanol reflux. That's another story. Methanol reflux is cheaper, of course, and you can do more samples at once. But if you really needed undamaged secondary metabolites, then this is the way to go. There's even some coffees are made with supercritical fluid extraction to get rid of the caffeine. It's very efficient, but it's expensive. Most caffeine is removed by water extraction. And then they send it to Red Bull and they put it back in the drinks. Or they send it to the drug companies and they put it in Excedrin. Okay, phase diagram from water is a little bit different. Okay, instead of having a positive slope between solid and liquid, it has a negative slope. So the solid here, so what does that mean? That means at any given temperature along here, if you increase the pressure sufficiently, you'll go from solid to liquid rather than from liquid to solid. Now, there was a time in my past when I said, that's a perfect explanation why ice skaters can slide easily across ice. Because with all their weight concentrated on that thin blade, they've increased the pressure to the point where they've got liquid between the blade and the ice below. So they just, but experimentation disproved that. There's really not enough pressure to do that. So we had to assign that ease of movement simply to the coefficient of friction between steel and ice, which is very, very low. But it sounded good in the beginning. Okay, so these various physical properties of materials can be explained in terms of increasing molecular forces between the molecules. If the intermolecular force will increase, what happens to the boiling point? It increases. Viscosity, if the intermolecular forces increase, viscosity increases, becomes less viscous. Surface tension, forces increase, surface tension increases. Enthalpy of fusion takes more heat to melt a solid if the forces are increased. Freezing point. Freezing point will also increase if the forces are stronger. Because you're holding things together, you have to get it warmer to make it melt. Vapor pressure, that's the one that runs opposite. Vapor pressure decreases as the forces increase. And heat of vaporization is also increased. So out of our list, the only one that's inversely proportional is vapor pressure. The rest are directly proportional to intermolecular forces. All right. Okay, so that takes care of chapter 10. Ooh, I've got to write that up here. In our textbook.